In this video, we're going to be going through some notes on momentum as well as reviewing through the problems that we should have done at the end of the Bill Nye video and the ESPN video. So the first thing I wanted you guys to do is, in your own words, describe the relationship between speed and momentum. Potentially give an example here. So you can pause the video if you want, and then come back and pause it when you're done with your in your own words description. But what I put is that as speed increases, momentum increases, right? Because momentum is dependent on speed, right? If you have no speed, you have no momentum. So for example, if we go back to the Newton's cradle, the ball moving has momentum, and then it passes its momentum into the other balls by hitting them. So that's one example. There are plenty of examples. Really, anything in motion would count as momentum. Number two, what is the other variable that affects the momentum of an object? When we're talking about that, we're talking about mass, right? Mass and velocity are our two variables that affect momentum. So what is the equation to solve for momentum? That is this P, or momentum, equals mv, or mass times velocity, right? We use P for momentum because m is already used for mass. Next one, if you were to add up the momentum of the individual pieces of the ornament after the collision compared to the momentum of the whole ornament before the collision, this is an example from Bill Nye, which should be true. If you added them all up, all the individual pieces, they should have actually the same amount of momentum as the ornament did itself before. We call this phenomenon the law of conservation of momentum, right? Conserving something means to save it. In other words, we're saving the momentum before and after. Cool. So now that we've kind of talked through that, hopefully we feel a little bit more familiar with these terms of momentum. I think that those things were pretty well clear, well explained in the two videos that you watched, but I just wanted to also explain them in my own way. And that way you guys have a sheet to kind of build your own knowledge there, right? To put it into your own words. The next one, the three different types of collisions. So there is an explosion, which we aren't going to talk too much about, but I did want to include, which is one object becoming many smaller objects, right? The ornament exploding would be one example, or like a grenade exploding, I guess, would be another example, where it's like one object becoming many. An elastic collision would be where they bounce, right? Elasticity has a bounce to it. This is where the objects do not stick together, they bounce apart. Inelastic would be where the objects do stick together, so they don't bounce apart. All right, that prefix in meaning like not elastic. So these are non-elastic collisions. I'm actually going to skip the two examples on page 3 and go through the Bug versus Bus momentum handout and then the Graney and Ambrose momentum handout. So if a moving car has momentum and it doubles its speed, I almost said it twice as its speed, it doubles its speed, its momentum will be twice as much, right? Or its momentum will be double. If two cars, one twice as heavy as the other, move down a hill at the same speed, if they are the same speed, that's really important, compared to the lighter car, the momentum of the heavier car is twice as much, right? Because there's twice the mass. The recoil momentum of a gun that kicks is the same as the momentum of the bullet it fires, right? We talked about this when we talked about Newton's third law. For every action, there's an equal and opposite reaction. So that's true again here with momentum. Number 4, if a man firmly holds a gun when fired, then the momentum of the bullet is equal to the recoil momentum of the gun and the man together, or the gunman system, right? Because now it's not just my mass or the gun's mass that's moving, but it's also like you move back while you're holding the gun a little bit, right? So that you're more massive, so the gun doesn't recoil as much. Or doesn't go backwards as much. Number 5, suppose that you are traveling in a bus at highway speed on a nice summer day and the momentum of an unlucky bug is suddenly changed as it splatters on the front windshield. Compared to the force that acts on the bug, how much force acts on the bus? It's the same amount of force on both of them. B, the time of impact. We'll talk more about impulse, but just know that they're the same right now. The time where they're impacting each other, force is the same. So the impulse should be the same. C, although the momentum of the bus is very large compared to the momentum of the bug, the change in momentum of the bus compared to the change in momentum of the bug should be the same, right? Because if we're applying the same amount of force there. D, which undergoes a greater acceleration. The bug under the same amount of force will exert a significant, or will feel significantly more acceleration, right? Which makes sense if we also just think about it in terms of the bus's speed does not change very much when it hits the bug, right? I mean, you don't even notice a speed change if you're going on the highway and you hit a bug, right? Whereas the bug was going, let's say, I don't know how fast bugs fly, like 2 miles per hour, and then all of a sudden it's going 70 miles per hour the other way. Right? That's a huge acceleration for that bug, and that's why it therefore feels more damage. The Granny and Ambrose one I really like because you guys have to kind of calculate some of these momentums before and after, which I think is going to be really helpful as we transition into the other problems on the ESPN video. But what you had to do before was you had to calculate the before collision momentum of Granny, Ambrose, and the total system here. So 80 times 3, or Granny's mass times Granny's speed or velocity, would give you 240 kilograms times meters per second. If we look at Ambrose's momentum, if he has no speed at the beginning, his velocity is 0, right? Because 0, or our speed times anything, will be 0. So our total momentum before is just 240. 240 plus 0, you get 240. So after the collision, right, they hit each other on these roller skates. Granny's speed will decrease. Her speed was obviously going to go down as she runs into something with mass. Ambrose's speed increases because it started at 0, so of course it's going to go up. After the collision, the mass of them together, Granny and Ambrose, is 120 kilograms now. So originally we just cared about Granny's mass of 80. Now we care about both of them, so 120 kilograms. And then after the collision, the total momentum of Granny and Ambrose, I didn't have to do a calculation for this actually. If I know the total momentum at the beginning is 240, I know the momentum at the end, again, has to be 240. So now, I'm going to use that knowledge to come on down here and calculate how fast they are going to be moving afterwards, right? So I know the momentum afterwards, the P here, should be 240. I know the mass was 120. So that should help me figure out the velocity. So I just have to rearrange this to get velocity by itself. So momentum divided by mass will tell me the velocity. 240 would be the total momentum after, and then divide that by the mass of both of them, or 120, and you should get 2 meters per second. So Granny slowed down 1 meter per second when she ran into Ambrose. Please let me know if you guys have any questions on this. I know this is a fairly straightforward problem, but these are the kind of things that I want us to be able to do by the end of the hour today. Finally, these ones are a little bit more complicated. The first one especially because I didn't realize that you have to convert it from a 10-pound ball to a 10, or to like what that is in kilograms. So I apologize for that. But you have a mass of 65 kilograms and you're standing on ice. You throw a ball forward at 4 meters per second. Calculate the speed at which you will travel backwards, right? If I'm on ice, I push a ball forward, so I go backwards. So P is equal to mass times velocity. The momentum of me at the end should be equal to the momentum of the ball at the end. In other words, my mass times velocity should be equal to the mass of the ball times the velocity of the ball. So 65 kilograms is my mass. I don't know my velocity, so I just left it as V. I did look up the conversion for this, and this is again why I apologize. It's a complex problem. It is 4.54 kilograms. That's apparently 10 pounds converted to kilograms, times the velocity of 4 meters per second. If you multiply those together and then divide them by 65, that should give you your velocity of 0.28, right? And again, that was me rearranging that equation. The mass of me on the other side, velocity is by itself now, so velocity is equal to 4.54 times 4. So the momentum of the ball divided by my mass will tell me how much I'm moving, which in this case is 0.28 meters per second. Mrs. G now. Mrs. G has a 2,075 kilogram van, and it runs into the back of a 825 kilogram compact car at rest. If it's at rest, again, zero momentum. They move off together at 9 meters per second. Find the initial speed of the van in meters per second. So first of all, this is an inelastic collision, right? They stick together at the end. And this time I'm going to use my knowledge that the momentum at the beginning should be equal to the momentum at the end, which in this case, the momentum of the van, the mass of the van, times the velocity of the van should be equal to the mass of the van plus the mass of the car times their velocity at the end, which in this case is 9. So I added the mass of the van and the mass of the car. Now I got 2,900 times 9, which is the velocity. Excuse me. They move at the end. Divide that by the mass of just the car, right? Because I needed to rearrange this equation to get velocity of the van by itself. And I get 12.6 is my velocity of just the van at the end. This is a little bit more complex of a problem. I understand that. If you couldn't understand how to do this, that's completely fine. We will talk more about that. Please let me know, though, how I can help you to fully understand this. So now we're going to move on to the interactive lab. Again, please let me know if you guys have any questions. Have a good one.